Today we'll be doing more on design of algorithms and running time analysis. So I'm going to walk through a few more examples that are there in that document that I've given. And I've chosen these examples to try to demonstrate a wide array of techniques that you can use. So we'll start today with a classic question of merge k sorted arrays of length n. Right, so you're given k sorted arrays, and I'm just going to call them A1, A2, up to AK, and you have to come up with B, which is the sort of the union of arrays. So this is of length n, and this is going to be of length n times k. This is the problem. We know how to do this when k is equal to 2. When k is equal to 2, it can be done in linear time. Right? So let's say this is the question that somebody asks you. Now, either in an interview or actually you have to do this as part of a project. The first thing, think stupid. Think about the most trivial solution you can come up with. The kind of thing that you can, sort of put down in 5 minutes. The trivial. And the reason I say this is sometimes it can be hard to beat the trivial solution. What is the most simplest solution you can come up with for merging k sorted arrays?
I have a quick question. A1, A2, is that basically just a list of a list?
It's a list of arrays. So now, the thing is, when we talk about algorithms at this level, often we'll use more mathematical notation. Your input is k sorted arrays called A1, A2, to AK.
The simplest solution would be just to repeatedly add two together, and you just keep adding to the main one, but it's going to get really long and kind of unbalanced for merging into second ones.
So you're saying take two of them, merge, then take the next one, merge, so on and so forth.
Yep.
Okay.
Yep.
So that is one trivial solution. You're absolutely right. I'll give you an even simpler one, which is even more stupid. Like, actually, your solution was kind of clever. Or at least you were thinking in terms of merge. Really, like, the dumbest thing one could do is to just put everything in an array and just sort it using merge sort. Right? This is almost ignoring the fact that all of these are sorted. So let's go over these trivial solutions. So I'll do mine first, and then I'll do the one that is suggested. So the first is copy all the arrays into B, use merge sort or whatever n log n sorting algorithm do you want, or any O of n log n sort on B. So what is the running time? Now let's be a little careful. The running time, so maybe let me write this down in the way that you should write it if you're doing this in the test. Right? So we'll say step 1, copy all the arrays into the output array B, sort B using merge sort. What is the running time of this task? This is just O of n times k. Just you have to copy everything. And what is this? This is O of nk log nk. right? And just using the properties of the logs, this is O of nk log n plus O of nk log k. So this is the first trivial solution, right? Copy all the arrays, just sort. Again, like in an interview, you can say this, even though you might think this is so obvious, just say it. Or when you're dealing with this, like if you're sitting in a meeting and you're trying to work this problem out, you can say, okay, you know what, the simplest thing we could do is this, because maybe coding this is really easy, which it would be, right? You just run a bunch of for loops and then you call a sort function. You're done. Okay, so this is what the running time you get. Any questions about this? Okay. Then the other solution that was given, and that's also a fairly simple solution because you know how to merge, so all you have to do is merge k times. Let's look at that. Like actually, let's analyze that solution because the running time is a little bit more complicated in that. So the idea is to repeatedly merge AI with the sort of A1 union A2 up to AI minus 1. Right? So it says once you've sorted the first I minus 1 arrays, you can then just merge AI with that. You're just doing repeated merge. Okay, so let's look at the running time of this. So let me write it down first. All right, so let's let's be a little careful with copying things. So I'll say the first step. I'll say copy A1 into B. By the way, so when you're doing these analyses, as you write pseudocode, it's fine to have off by 1 errors. It's fine to have slight errors in syntax. It's fine to have like off by 1. Minor errors we will usually ignore. Okay? We are going to use our judgment to try to understand what your algorithm is. So the first step is to copy A1 into B. Now the second step is now going to be a for loop. Right? It's going to be a for loop. So I'll say for I going from 2 to k. Maybe I'll just open up a braces over there. So I'm just going to merge AI with B. Okay, and this needs to be merged. When you do a merge, you merge it into some other array. So what I'm going to write is maybe not the most efficient way of doing it. You can make it more efficient, but asymptotically in terms of big O, it'll be the same. So, merge B with AI into an array C. Then you just copy C to B. That's it. Okay, so this is 2A and this is 2B. Does this make sense?
Yeah.
Okay, so what is the running time of the first step? That's just O of n. What is the running time of this step? Now this we need to think about. The running time is really the O of the length of AI plus the length of B at this stage. Now the length of AI is just n. The length of B, if you think about it, is actually going to be a little bit, it's going to keep increasing in size. And it's really just I minus 1 times n. Right? Because when you initially start, it has length n, then it has length 2n, then 3n, 4n, so on and so forth. And copying C into B, this is again going to be just O of, in this case it's going to be O of C, and this is just going to be O of I times n. So essentially, steps 2A and 2B take O of In time in the ith iteration. Total runtime is O of the sum over I of n. I is going from 2 to k. And using the things that we've discussed so far, this is going to give you O of k square n. Or maybe I'll just write this as O of n k squared. Okay? So what we now have is we have O of nk squared versus O of nk log n plus nk log k. This is what we had by just taking it all together and sorting it. It should be like the simplest thing to do. And it's not clear which one is better. It actually depends. If k is smaller than log n, then this is better. But if k is more than log n, then actually this one is worse. Any questions about these two simple solutions? So for the purposes of the test, if this is what you wrote, if you simply wrote this and you said this is the total runtime, like, okay, that's it. That's all I want. Any questions?
Yeah, can you, I guess, go into a little more detail on how you did the total running time? Because I'm looking at that.
Sure. So
Really confused on how you did that.
So let's look at what is the runtime of merging B with AI into array C, right? This, by the properties of merge, is O of AI plus O of B. It's like it's just linear in the length. Right? They take this time by the linear time merge. Remember, we said if you have two sorted arrays, both of these are sorted. These are both sorted. And this is also sorted. They're all sorted arrays. So the running time to merge two arrays is linear in the sum of the lengths. AI has size n for all values of I because we're merging n arrays of size, k arrays of size n. B is going to increase linearly as I progresses, right? As you have more iterations, you've accumulated more and more. So you get I minus 1. I minus 1 times n. So the length of AI plus B is just I times n. So steps 2A and 2B take O of in time in the ith iteration. The total runtime would be the sum over all the iterations. So I sum over all the iterations. And I go from, I'm summing over I going from 2 to k of I times n. And then I know that the sum is, remember, I mean, this is at most I going from 1 to k. And we discussed what this quantity is. Right, this is basically k times k plus 1 divided by 2. So this is basically O of k squared. This sum is just at most k squared. Yes?
Hey Sash, why do you have to copy C into B? Why can't you just leave it in C and use C?
You could be more efficient. Then next time you'd have to use C and then merge it into B, right? You need extra space. I'm just writing this way so that it's more convenient. You're right that you could save on some of it, but you'll see that regardless of what you do, you'll still end up with nk squared. You won't be able to avoid this because this is the running time of the merge.
Right.
Okay, so the K-squared came from the summation formula, right? That's what you're saying?
I'm sorry?
The K-squared came from the summation formula?
The K-square comes from the summation. It basically comes from the fact that you have to merge all the time. Right? So you have to keep additionally merging.
Right, that makes sense. Okay, thank you.
So this gives you the runtime O of nk squared. Okay, so this is another solution. Now let me give you a third solution. And then from the third we're going to go to a fourth solution, and then there's going to be a fifth solution. Alright? Give another solution. Now let's actually dig into the merge procedure. So if you recall, there are k arrays. This is A1, A2 up to AK. We could think of, I have a pointer I1 or an index up to IK. Right? I have this index I1, I2 to IK. I find the minimum from that, copy that to B, and then advance that pointer. So when you have merged, you just had this. And then what you would do is you would basically see which of these A1 I1 smaller or A2 I2 smaller. The smaller one gets copied and then I1 would advance. But you could extend that argument to K. So let me now write this solution. So I'll just say initialize. So step 1 is initialize indices I1, I2 to IK equals 0 and I of B equals 0. Then I can do the merge step. So you don't really have to number necessarily. You don't need to number it. I'm just numbering it so that I can go and refer to that statement more easily. So I'll say Y IB is less than NK while it's less than the total. So I'll say find the minimum among A1 I1, A2 I2 up to AK IK using a for loop. So this is important because how do you find the minimum? You have to tell me how you're finding the minimum, because finding the minimum in these is not a constant time operation. Then I'll say copy the minimum to BIB and increment corresponding index. So what that means is you copy the minimum and then you increment that increment or corresponding or the min index. Right? So one of these indices is going to increment. So this, I'll call it is, this is step 2A. This is step 2B. And then step 2C will just be IB++ or increment IB, whatever have you, and this would be the algorithm. Does this algorithm make sense?
So you're going through each array one step at a time and then taking the minimum of each array, but you would only increment the one array that you took it from, right?
Yes.
And the other arrays haven't incremented yet?
Exactly. Yeah, that's what this means. I'm sorry if I didn't write this out in full detail, but
no, it's fine. I'm just clarifying.
Yeah, I know. So
that's what you said. I just was making sure I understood it.
Yes, that's right.
Is my intuition right in that I'm kind of seeing selection sort here?
Kind of. I mean, it's not really selection sort because it's really generalizing the idea of merging arrays using using these indices. Like if you think about
it,
I'm sorry? Go on.
I was just wondering, this is like exactly the same as merging two arrays, right? And we're just applying the same method but to more arrays.
Exactly. So if k is equal to 2, this is the old merge procedure. I have generalized that to k. Like if you just had k is equal to 2, then you would find the min of A1I1 and A2I2. You copy that to B, and then you increment one of those indices.
Instead of using like a for loop to find the min, could you use like a min heap?
Okay, good. So you're jumping ahead. Good.
Okay.
So right, but this is how you sort of get there, right? You say, okay, let me now write down this procedure. I want to write down the runtime analysis of this. What is the runtime of this step? O of k. What is the runtime of this step? O of k. What is the runtime of this step? O of 1. O of 1. Now let me do the running time analysis. Let's do the running time analysis. We'll say that steps 2A, 2B, 2C. Sorry, just so steps 2A, 2B, and 2C run in O of k. The loop in step 2 runs nk times. So the total running time is O of nk squared, and step 1 runs in O of, or the total run times for step 2 and runs in O of k. So the total running time is O of nk squared plus k, which is just O of nk squared. I don't want you to leave things at there, because if you ever write this, then someone's going to think you don't understand what big O notation is, right? Always make sure you simplify it down. Never write this. I mean, never end at that. You can write this and then go further. Okay, so it's really important that you don't write things like O of 2 times k, even though it's correct. What it suggests is you don't understand that the 2 can be subsumed by the O of k, so you write this as just O of k. Always simplify it down. Okay, so that gives you nk squared. So this is interesting that there were two different methods, two different approaches that both gave you O of nk squared. And now, as someone already suggested and someone has jumped ahead, you start thinking, how can you improve the solution? And it's whenever you're doing a search, like some kind of linear time procedure, you think that's where I need to do an improvement. So I need to find the min of a bunch of quantities, and the perfect data structure to find a min amongst a set is a min heap. Okay, so I'll write the solution down, but I want to say this verbally and take any questions. You want to find the min amongst these. So what you do is, suppose all of these were stored in a min heap. Then what you need to do is an extract min. Now when you increment the corresponding index, you now have to insert a new element into the heap. So the copying is going to be, so getting the min is an extract min. You remove it and then you put a new element in the heap. So you can essentially replace this operation, the first operation is just going to be an extract min, is an extract min. The second operation, you copy it and then you do an insert into the heap. You insert from the array. Okay? And so once you do that, you can basically keep track of the min heap, and these operations go from being O of k to O of log k. And you'll actually get that it's going to be O of nk log k. So I will write, but any questions at this point?
To build the heap, there will be like an additional O of k, right?
The initial part?
Yeah, to build the initial heap.
To build the initial heap would be like O of k. Yeah.
Okay.
I mean, even if it was k log k, it would still be okay. But yeah, the initial build heap would be O of k.
It sounded like you were saying to make a heap for each array, but why not just make one big heap and throw it all into that heap? Because then you're almost all the way there.
So you're saying put all the elements into a heap.
Yeah.
Well, then
rather than make a bunch of little heaps.
There's only one little heap. Now here's the okay, good. So that's a good suggestion. If you put everything into one big heap and you sort, you're just doing heap sort. Right? That's what heap sort is doing. You just put everything into one big heap. The problem is the running time for an extract min is log of the size of the heap, and the heap is n times k when you put everything into a heap. In this case, the heap is really tiny. Therefore, operations on the heap become fast. If you put everything into one big heap and then you just keep doing extract min, you will end up with the same running time here, because you're effectively just doing heap sort instead of merge sort. So I'm going to write the solution down. So I'm going to write this down a little carefully, just so that we see all the details. Create a min heap with objects. So there are going to be objects that are pairs, and you'll see why. A of 0, A1 of 0, 1, A2 of 0, 2, A3 of 0, 3, so on and so forth. AK of 0, K. So I'm going to put pairs. I'm going to put pairs where I take the first element of each array, but I also tack on the index of the array that it is from. This is from the first array, this is from the second array, so on and so forth. So I'm going to tack that on with the first element as the key. So the key is actually the first part. Okay, so you create a min heap with these pairs. Okay. Then I initialize IB being 0. And then I'll say for IB from 0 to n times k minus 1. So open my braces here. Step 3a is extract min. So create a min heap that I'll call h. Extract min from h. Let it be, so it's going to be a pair. Let it be, so I'm just denoting what the pair is. The pair is, I'm just going to call it val, comma, j. It's going to be a pair where there's a value and there's a j. There's an index. 3b is to set b of ib equal to val, and I'll also say increment IP. I'll just put it in one line because just to sort of save space. Now you got the index over here. What is the element you need to insert?
J plus 1.
Which one?
J plus 1.
So this is the problem. It's not J. J is actually the index not in the array, but index of the array. So I deliberately did this because now we're going to go back and we're going to have to fix this algorithm. We actually have to keep track of which index we are removing. So actually, instead of pairs, it's going to be triples. We put 0 as an additional element. So it's basically what this is it's value index in the array and the index of, or this you can think of as which array, right? So I'm keeping pairs of triples. So instead of this, it's going to be, you can think of it as val. There's some value. There's some index that I'll call ind, and then I'll call it j. So this is what you get out. Then what you do is you insert aj of the index plus 1, the index plus 1, and j into h, and that's it. So the way to think of it, you just draw a picture. So at some point, let's say this is in the heap, this is in the heap. There is only going to be one element from each array in the heap, right? And this is what the heap is going to have. So we're going to extract the max. So we're going to remove this, or extract the min, I'm sorry. Remove this and rearrange the heap. And let's say this was some element here, part of this array. What we now need to do is take the next element and then stick that back into the heap. And so the extra indices and the other things in this object are basically keeping track of which is the next element to insert. Any questions?
Where do we use J?
We use J to determine, so you extracted val, but which array did val come from? That's what J is. So it's used over there.
Okay.
So val tells you, J tells you which array, and the index tells you which index in that array.
So essentially, we do this till the heap is empty, right?
Well, yes, you do it until the heap is empty. I mean, okay, so there is a corner case there that usually what this says is if ind is more than n, then there's nothing to insert. Or you could think of if the last element is sort of always in, like you can always tack on an extra infinity at the end. Right? And so you only have to do this nk minus 1 times, because every time you do it, you get a new element to the sorted in the output. So these are the kinds of things that if you didn't mention in your pseudocode, it's completely fine. You're missing a corner case, that's okay. Because we're talking about algorithm description and development, not about explicitly converting to code. Now, when you convert to code, yes, the corner cases are important. And to me, that was the first part of this course, to try to train you in that. But now, I accept, that you know how to do that. You have some training in that. Now it's time to think at a higher level. When you convert this into code, then obviously you have to consider all these corner cases, and that's important. But that's not important when we're trying to figure out what algorithm to use. And we're trying to understand the running time of the algorithm. At that point, these corner cases are not important.
So you have to repeat this process for every, starting at the first element of the arrays and then moving on to the kth element. Is that correct?
No, you don't have to repeat it k times. This is it. This is the algorithm. So think of it as...
When we initialized our heap, it just has the first elements though, right?
It only has the first elements, exactly. But as this proceeds, it will take more and more elements of the array. The heap only has k elements at every point because there's an extract and there's an insert. So the size of the heap remains k.
Oh, I see that 3C, thank you.
It's a little tricky, right? You have to think about it a little bit. It's not as obvious as the other algorithms. Any questions about what's happening here?
So why do we need J? Like, I understand it's which array it is, but we have the array stored in already.
So when you extract the min, how do you know which array that min came from? So the heap has one element from each of the arrays. You extract the min from the heap, but how do you know which array it came from?
Oh, okay. The heap only stores the values. I thought the heap also stored the index.
But that's exactly what it's storing here. It's storing the index of the array.
Okay. Sesh, but this would only work if you have an array of arrays, right? Because all these like sub-arrays that we're merging together, they don't really have an index assigned to them. I assume they had different names.
I mean, if they have different names, then you put the name over there, right? Or you know, this is again a sort of coding detail.
Okay, so J is just like a placeholder so that you know which array it is.
Exactly.
It doesn't really matter how you implement it.
Exactly. Like probably if you were to implement it, then you would probably maybe put everything into like a 2D array, or you would make it like a linked list of arrays, and then this would give you a pointer. You know, you could do any of these things.
Yep. Thank you.
Right, and essentially what I emphasize is during the course of algorithm development at this level, it doesn't matter which form you have, and it also is okay for you to assume any one of them and just write down, this is what I'm assuming the input looks like. If that makes sense. Because in the way the questions are described, and often, you know, even in interviews or various settings, they won't tell you how the input is specified, so you make a guess. You say, I'm going to assume the input is specified in the following way, and then write your code accordingly. And then they might say, well, no, your input is actually specified in a different way, and then you have to adapt. But always go ahead and pick some natural or reasonable way it's specified. Just as you suggested, maybe it's a 2D array.
I have a quick question. So what if each individual array was not sorted? So we first have to, would that be...
so that in some senses, but that's the assumption of the problem. You're merging case sorted arrays. That's where we're starting. If they were not sorted, then you wouldn't be able to merge.
Okay, that makes sense.
If they were not sorted, then all you can do is the trivial solution of copying everything into one array and just merging it.
Okay, that makes sense.
Okay, so does this make sense at this point? Any questions about this? So the running time of the first step, and then I'm going to write down the running time in more carefully. This is O of k. Sorry, let me write down the running time over here on the left so you can see. This is O of k. To create a min heap with k objects is O of a. You put it in an array and then you run build heap. This is O of 1. Okay, now let's look at these steps. This is O of log k. O of 1, an O of log k. Sorry, it's sort of squished over here. And so therefore, step 3 will become, I don't have enough space here, so write it down there. It becomes O of nk log k. So instead of nk squared or nk log n, you get nk log k, which is actually the best of, which is better than both of those bounds. Okay.
And that's because the for loop goes to nk.
Exactly, because every time you extract, you do this operation once. So again, I'm going to write this down properly so that you can see what's going on. And I would like you to write, the way that I wrote this solution is kind of the level of detail that I would like when you write your solution. And that's because so that I understand you exactly. Usually, if you're in this process, either with other people or with an interview or whatever, you would write, then someone would say, why don't you give more detail there? And then you could get into more detail. So it's different if it's interactive. In this case, because you're just writing a solution that I can't interact with, give me this much detail. So now let me write down the running time analysis. So it's very useful to do it step by step. You say, okay, so step 1 runs in O of k by the build heap procedure. This is standard, so you just say that's what it takes. Step 2 runs in O of 1. Steps 3a and 3c run in O of log k by the min heap properties. And you say step 3b runs in O of 1. The loop in step 3 runs for O of nk iterations. So the running time is O of nk log k, right? Because 3a and 3b run for that. Total running time is equal to O of k plus 1 plus nk log k, which is O of nk log k. Good. The tombstone symbol is a common symbol to indicate the end of the proof. So good. So we're done with the proof now. This gives nk log k, which is actually the optimal algorithm for this problem. I'm going to sketch out a different optimal algorithm, which also gives nk log k using divide and conquer now. Okay, so first let me make sure. Do you all understand this? Does this make sense?
Yes.
Good. Okay. Now let me give you a different algorithm. So this is, remember, we started with the trivial solutions, and we had like 2 solutions that gave nk squared. So the first was just trying to apply the merge algorithm, and we improved it by using a min heap. That gave nk squared. Another algorithm that gave nk squared was repeated merging. It turns out that if you apply divide and conquer here, you also get nk log k. And it gives a very different algorithm. So let me describe what that is. So let us consider the input as a 2D array of size running out of ink. Of size k cross n, right? Right, so each of these is sorted. Each of the rows are sorted. So what was the strategy that was suggested? It says, okay, take the first row and the second row, merge them. Then merge it with the third. Then merge it with the fourth, so on and so forth. But what if you did divide and conquer? So how would divide and conquer work? It would say, split A into A, I'll say up, which is of size k over 2 cross n, and A down, which is of size k over 2 cross n. So split it this way. And so you get the upper part and the lower part. Okay? Recursively, so using divide and conquer, so just recursively sort of solve A up to get the array B up, and solve A down to get B down. Or I should say this is step 2, step 3. Recursively. So just use recursion, divide and conquer. So it says split it into 2 parts. That's a subproblem. Recursively solve it. Then finally merge B up and B down to get the output. I'll say the base case, if k is equal to 1, just return A. Right? If you have only one array, just return one of them. Any questions about this?
So, like, can we understand by this, like, you only merge when the two parts are in the same size?
Exactly. You merge them when they're in the same size and you'll get an improvement in runtime.
Okay.
It's exactly the right point. Because the problem with the other case was that you're merging a small array with a big array and you repeatedly pay the cost of the big array. But here you try to merge things. It's almost like you're doing multiple merges so that every time you put two piles together, they're of the same size.
This will, however, cause more merges than the previous one, right?
Interesting. Which previous one?
Sorry, the previous one where we merge like a small array with the big array.
Mm-hmm.
And then, you know, because that one we're doing a merge, I believe, k times,
Mm-hmm.
or k minus 1.
Mm-hmm.
Whereas this one, that would be more.
You'll actually get
correct?
this. You get the same number.
Oh, okay.
It's a good question. You have to think about it a little bit. If you draw out the recursion tree, you'll see it's the same number. I'll draw another picture for you that should clarify that. But that's a good question.
Okay,
It turns out to be the same. Okay. Let me first do the runtime analysis, and then I will explain this other point. So how do you do the runtime analysis? So note that n is sort of fixed, right? In all of these recursive calls, it's k that's changing. So let tk be the worst case runtime to merge k arrays. The runtime of the first step, this is actually just O of n, like if k is equal to 1. Okay, so the runtime of the second step is O of k times n. The runtime of the third step, that's t of k over 2. The second and third step is t of k over 2, and this is going to be O of n times k. Sorry, I should have said O of n times k instead of k times n. So the recurrence that you get t of k is at most 2 times t of k over 2 plus O of nk. N actually doesn't matter here. So you can, the n is like a constant. It's a constant with respect to the recurrence. So it kind of goes out of the recurrence. But this is exactly like the merge sort recurrence. And so you get that t of k is O of nk log k. Right? So this appears a lot. You take a problem, you split it into 2 parts, solve each of them, and then you have a linear time combine. This was the divide, and this is the combining the operations. This also gives you nk log k, just like the previous solution. Let me give you another picture to think about this, and that might help. So one way to think about it is you have these k arrays. So what you do is, instead of trying to merge in a loop in the following way, you first merge these two. Then you merge these two. Like you merge these two, it becomes a big array. Merge these two, it becomes a bigger array. You merge those two. So this, it'll become twice the size, then 4 times the size, so on and so forth, until finally you merge 2 things and you get one big array. If you count how many merges happened, it'll be exactly k minus 1. Assuming k is a power of 2, you get exactly k minus 1. Okay, because you have to keep track of how many merges. So in the first step, there are k over 2 merges. The next, there are k over 4 merges. Then k over 8 merges, so on and so forth. So this is an alternate method to also give you nk log k. Any questions?
Josh, can you go over the time complexity analysis of this again?
So your array is of, let's think of it as a 2D array of size k, like k times n, right? Or you can think of it as it's k arrays of length n. So the algorithm just says, you're doing divide and conquer. If k is equal to 1, you say, okay, just return a. Otherwise, you split a into the top part and the bottom part, the up and the down part. You recursively solve the up part to merge it into a sorted array. Recursively solve the down part to get another sorted array. So you get b up and b down, which are both sorted. Then you merge those to get the output. Now for the runtime, we say, okay, let's go over these steps one by one, but because it's recursive, we have to define some t of k. Now why don't I do t of k and n? And you'll see that n is the same for all the calls. N doesn't change. It's k that is changing. So t of k is the worst case runtime to merge k arrays. The 0th step, the base case, that's just O of n, right? It's just checking if k is equal to 1. Actually, it's even constant. It's just O of 1, really. The second step is to split into up and down. And again, with pointers, you could be more clever with this. I'm just saying, suppose you went ahead and you just linearly copied it into 2 separate chunks. So that's just linear in the size of the input. This can be done in O of 1 if you're careful with your pointers. Now recursively solve the top part. So you're recursively solving this, which is just t of k over 2. Because that's the worst case runtime to merge k arrays, and you're merging k over 2 arrays. And here it's t of k over 2 because you're merging k arrays. Then you merge the outputs to get a single array. But this is, you're just losing linear time merge because the size of b up is actually going to be kn over 2. And the size of b down is going to be kn over 2. So merging those is just going to be O of nk. And so that gives the recurrence over here. Because you just sum all of these things up, sum all the runtimes, and t of k is at most the summed runtime. And to solve this recurrence, again, if you ignored the n, you basically get k log k. And you can actually just multiply by the n. If you want to have a different picture in what's going on, I think the tree is very helpful. You start by merging pairs, then you merge pairs of pairs, and then pairs of those, and so on and so forth until you get the final output. So, any questions? Do you want to see me do more of these? Let me just poll you and ask. Red is yes, I want to see more of these, and green is no, we can move on to something else. If you want to see more of me solving different problems like this.
Do you mean other problems or
other problems?
The same thing, doing another version of the same one?
No, so I'm done with this problem. Another couple of problems.
Okay.
So not this problem, but I'll take up maybe two more problems that have been given, one or two more problems that have been given, and discuss those. All right, I think there's a clear plurality of people who would like to see more of this, so I'll go ahead and continue. In the interest of time, and because I want to show you as many problems as possible, I might not give all the details, like on how to write down everything step by step, because I've done it for one problem. Because I want to show you as many problems as I can. If there are doubts, again, stop me, as I'm talking about it, and I'm happy to give more detail as and when necessary, but I will start. Initially, I'll probably give less detail. Okay. So let me pick up another very nice problem. And this is to find a local minimum of an array. So what is a local minimum? So it's an array A. Okay. I is a local min if a of I is less than equal to a of I plus 1 and also less than equal to a of I minus 1. We'll assume that a of 0 and a of n minus 1, the ends of the arrays, we'll assume they're infinity. Right? So the way to think of this is like, if you want to think of the array as a function, imagine that I'm plotting. So this is the index going from 0, 1, 2 to n minus 1, and this is a. I'm just going to put the values here sort of at infinity. And you could imagine like just connecting them by a curve. Right? This curve could do lots of things like this. So that's a local minimum, that's a local minimum, that's a local minimum, that's a local minimum, that's a local minimum. So a local minimum is simply a value which is less than or equal to its neighbors. And because I set a of 0 and a of n minus 1 to infinity, I'm guaranteed that there will be a local minimum. Okay? And so this is the problem. Find a local minimum in an array. Okay, is the question clear?
There you have greater than and less than with equal signs.
Yes.
Wouldn't it not be a minimum if it was equal to the other ones, or?
It is. I mean, if you didn't put equal signs, then a minimum might not exist. A minimum doesn't mean it's unique. It just means it's lower than equal to everything.
Okay.
Right? Because otherwise, then I would have. It's usually called a strict minimum versus a normal minimum. This is to ensure that there's always an output. If all the values are distinct, then of course you can remove that.
So if all the values are the same, does it mean every value is a local minimum?
Then every value is a local minimum.
Okay.
So think of it like you're trying to minimize a function and you just have to provide a value that's the least. Okay, so you get a problem like this. always start with brute force. Brute force solution is really simple. Let me call this condition 1. Single for loop checks 1 for all I. Right? And so this running time is O of n. Simple. And so now the question is, how do you beat O of n? And the problem is, there's really no data structure that you can throw at it, because if you try to put everything into a data structure, it's going to cost you O of n. And so when you have a problem of this form, where you actually have a linear time algorithm already and you're trying to go below it, your main tool is try to get some kind of binary search type procedure out. Or another way of putting it is to do divide and conquer. So let's do divide and conquer for this problem. And it's a little subtle. So here's your array. I want you to ignore indexing issues, even, odd, things like that, to understand the main picture. So let's start with A of n over 2, which is what we would do in binary search. We can check if A of n over 2 is a local minimum. If it is, then we're done. If not, then what? Maybe I'll draw the picture here as well. So you looked at the value of n over 2, you got some value here. It is not a local minimum. So it is not a local minimum. So maybe the value nearby is there and the value over there is there. Then what?
Then do we check n over 4 and 3/4 of n?
So if you did n over 4 and then n and then 3/4 n, and you kept doing all of them, then you'll effectively check everything. If you think binary search, you need to make one recursive call, either to the left or to the right.
Check the smaller value next to a n over 2.
So check this value, you're saying. Okay,
yeah.
And suppose that isn't a local minimum. Then you go to the next value, and the next, and the next. Suppose all of this was decreasing. You'll end up with linear time yet again.
Maybe divide the left in half and compare it with a of n over 2.
Well, I mean, comparing it with a of n over 2 isn't going to buy you, and the a of n over 2 is the end, right? And local minimum doesn't have anything to do with the, well, comparing a value internally with a value at the end doesn't really help, because the only condition you need to check is with neighbors.
Right.
You could take a shortcut in which, since n over 2, the one to the right of that is, we know that one's not a local minimum for sure, so we can skip that one.
Okay, you can skip that one and go, you can skip, but what if this was actually going up? So you would skip this and go there, and then you would skip that and go there, which means you're skipping every other one, but it's still going to be linear time.
Should we compare n divided by n divided by 2 with n divided by 2 minus 1 and n divided by 2 plus 1?
So that you've already done, because that's what it's doing, this check, right? If it was a local minimum, you're done. So to check that this is a local minimum, you've actually just checked these values.
Oh, compare n divided by 2 minus 1 with n divided by 2 plus 1 and pick the lower one.
Okay, so the smaller one is this one. Then what?
Do n divided by 4.
how does n? Okay, why n divided by 4?
Because then we divide the array yet again.
So what's the idea? The idea is that, okay, so you're here. You're going to split the array into 2 parts. How do you know which one has the local minimum? You know that there exists a local minimum somewhere. There has to.
Professor, so like, why does it have to exist one? What if the
Your
it's
answer
like
infinity.
monotonically increasing? What if it's forever increasing?
Because of the ends,
Okay.
it's not monotonically increasing. Another way of defining this is to say that if you're at the end, then you just check one condition, if that makes sense. And if you're at the end, just check one of the conditions, whichever one exists. But technically, it's because of this, right? For the ends, I'm just saying that you just have to check one of the conditions, not both.
You could check if n over 2 minus 1 or n over 2 plus 1 is, like, whichever one's smaller, you divide in that direction.
Why?
Well, like in the picture that you have, if the right side is just going up, you know that the min would be on the left side.
Sure, but the right side might not be going up. I mean, the right side might be doing this. You don't know, right? Over here, all you did was check 2 values. Maybe the right side is going to go down.
But we know for sure that there's going to be a min on the left.
Why?
We don't know because it goes down. If it goes down all the way, then there's a minimum. If it goes down and then back up, there's a minimum. Because it went down compared to where we are.
So can you formalize that thought?
Formalize how?
State it mathematically, right? So there's clearly, you said that if you go to the left, you're guaranteed that there's a local minimum. So what you're stating in some sense is a mathematical fact.
Yeah.
Right? Because we said that the right side may or may not have a local minimum. But the left side definitely has it. So that's the key idea. So that, what you have pointed out, is the idea.
Do you find which side has a lower value, cut it in half, and take the side that has the lower value and do the same thing on the left half? Or whichever half you choose?
So let's step back. So what was proposed is the solution, right? So whatever was proposed said that go here and find a local minimum here.
Can you go from the left side, like, can you start from 0 and then kind of move to the right, and as soon as you find a value that's greater than n divided by 2 minus 1, you know the local minimum exists in the range.
But why do all of this when you can just do it recursively?
How do you do it recursively?
You basically just do it recursive, write a recursive procedure, and what was suggested was exactly that. And whoever said that said they got the right idea. They said that the local minimum lies in the left side. There exists a local minimum on the left side. Why? That's the question, right? Once we address why that's the case, then that's it. We have our complete solution.
So like if you want, how to say that? If you like have 2 points, and you are decreasing, and there has to be a local minimum because they are happy to increasing with that point.
So, okay, so you're making it more formal. What you're saying is if you have an array such that both of the ends are actually increasing.
Yeah, right.
Then there must be a local minimum somewhere in between.
Yes.
So let's state this as a fact. And once we have this fact, we'll be done. So consider any portion of the array A, I going to j. And suppose AI is greater than or equal to AI plus 1 and AJ is greater than AJ minus 1. Then there exists a local minimum in AI to j. This is basically like a mathematical theorem. You can prove it. Prove it by induction. You can prove it by induction because you can actually very easily see that either AI plus 1 is a local minimum or AI plus 1 and j satisfy this condition. You get a proof by induction. You get a proof by induction. Okay? So now let me give you the algorithm. So the algorithm, and I'll write it a little bit more formally so that you see the idea. I'll call it local min A, and we'll take two parameters, start and end. And we guarantee that A of start is greater than or equal to A of start plus 1 and A of end is greater than or equal to A of end minus 1. I'm not doing corner cases. What if start and end had a difference of 1? What if they were the same? Sort of going to ignore these conditions. So sort of for the base case, I'll just say that if end minus start, just to deal with 4 is just an arbitrary constant, then find a local minimum using brute force, which you can do, right? Because it's just 4 elements, so this is just going to be something that's O of 1. Then check A of start plus n divided by 2. So I'll call this mid, A of mid, with A of mid minus 1 and A of mid plus 1. So just compare, just check or compare. If A of mid is a local minimum, okay, then we're done. If not, then if A of mid is strictly greater than A of mid minus 1, then you return local min of A start mid minus 1, else return local min of A of mid well, actually I'll say, sorry, mid, A of mid, and end. That's the procedure now. Okay, and these are all O of 1 operations. The only thing is a recursion, and you'll see that the recurrence is the same as binary search. And so what you get is that T of n is less than T of n over 2 plus O of 1, and T of n is O of log n. Okay? So the heart of the key idea is to really consider any portion of the array and realize this theorem which says that if AI was more than if the ends are more than their neighbors, then there's a local minimum somewhere inside. And as long as you zero in on a region with a local minimum, eventually, you'll be in a constant size array and you can just go ahead and find it. It's a trickier problem. It's not that easy. The code in the end is not that hard to write, but the idea really requires a lot of cleverness. And you're saying, how am I going to discover something like that? And again, the key is, remember, you start with brute force. You recognize you're doing linear search. And for a linear search, you need to do some kind of binary search. And the way to get a binary search is divide and conquer. Split into two parts and look at one of the parts. And once you walk down that path, right, you'll get to the solution. With experience, you'll get there, but these are the tools. This is the way you think about these things. Once you get O of n, you want to get O of log n. And O of log n you're going to get by some kind of binary search. Any questions?
So, if your array was sorted increasing, would that be the worst case, and the first element would be the local min?
If your array was sorted, then that would probably be the worst case, right? You would basically you would start at n over 2, you go to n over 4, n over 8, so on and so forth until you get to the end. Or even if it was, sort of convex. Like suppose there was only one local minimum, which was a global minimum. You would also have a similar situation, which is kind of what you were talking about. The worst case is when there's one local minimum. Any questions? Any questions? All right. I'm now going to talk about one other problem. Of course, there's only 10 minutes, so I'm not going to have time to do the entire solution. But what I want to do is I want to sort of indicate the main ideas, and then I'd like you to go and work out the solution by yourself. And I think by working it out, you'll sort of really understand, it'll give you a better understanding of divide and conquer. So this problem is also sometimes referred to as the stock market problem. So it says, given an array of prices, think of it as each day has a different price. Given an array of prices where each day has a different price, what is the max profit that can be made by one trade? So let me explain this. So you have this array A. So you have to buy 1 unit of stock and sell it. So if you buy on day I and sell on day j greater than I, the profit, or I guess, yeah, the profit is AJ minus AI, which could also be negative, which means it's a loss. Right? So AJ minus AI. So the problem is, again, now if you ignore, the reason I'm sort of describing this sort of stock market situation is to tell you sometimes a problem is stated without there being any reference to, well, in this case there's an array, but you might think of a list of prices, and it sort of talks about something in terms of English, and you have to convert it into a more mathematical computer science language. And what you could say is, find the pair of indices I less than j such that aj minus ai is maximized. That's your problem now. Find the indices I less than j so that aj minus ai is maximized. Brute force solution, which is quite simple. Please think about it. Gives running time theta of n squared. It's O of n squared theta of n squared. And now you want to improve on this. This is a place where, again, you could think divide and conquer. So I'll sketch out the basic ideas. I want you to go and work out the solution yourself. So here's your array. Here's L and R. So you can say recursively find best profit in L. Recursively find best profit in R. So let's say you recursively find it. How do you combine? There's one situation that's left. And what is that situation?
You buy on the left side.
You buy in the left and sell in the right. Exactly. Right? So this is exactly the situation that's left. What if you buy in L, meaning that I is less than n over 2, and sell in R, which is j is greater than or equal to n over 2. How are you going to solve this? And it turns out this can be determined in linear time. Because if you're buying in the left, you would buy on the cheapest day in the left, and you would sell in the most expensive day on the right. This can be solved in linear time. So you recursively find the best profit in the left, you recursively get the best profit in the right, you determine what happens if you buy in the left and sell in the right, and then you take the maximum of those three. And this gives a divide and conquer solution. And that divide and conquer solution, if you write down the recurrence, you'll get this. This is for the two recursive calls for the left and the right. And the O of n is to solve the last part, where you buy in the left and sell in the right, and then you combine it to get the max profit. And if you solve this, again, what you get is that T of n is O of n log n. This is not that easy, right? You have to sit down and write it out. But if you write it out, you will see that using divide and conquer, you can get T of n being O of n log n. There also happens to be a solution that gives O of n, which is trickier. You can do it through divide and conquer, or you can actually even do it through a straightforward for loop, but you'll have to think about the right data structures. But you can compute the optimum, the exact max profit in O of n. But as I said, O of n squared is brute force. Make sure you know how to write that down. Try to get n log n using the idea I just described. And if you get it as a challenge, you can try to get an O of n solution. So I'll end here, and I'll take any questions that you have.